Now that we've gotten the statement of the product rule and we've verified that it actually works by looking at the proof, we are going to look at some examples here in which we differentiate, take the derivative by using the product rule, and then we can verify that these came out correctly in some cases by using the power rule as an alternative. So let's see what this looks like here. All right, our first example is going to be the derivative with respect to x of x cubed minus 8 times x squared plus 4. Okay, now if you got that problem and you weren't told to use the product rule, you might say, hey, I can just distribute that out and then it's a power rule thing. That's how we're going to do the verification. But we want to practice using this new thing. We just got the product rule. Let's play around with it. So here we've got our f of x, the first function, and g of x, the second function. Okay. And I tend not to refer to those so much as f and g. I tend to call them first and second, just because that's how I have it memorized. Because it doesn't really matter which one you call f and which one you call g, as long as you have things in the proper order and put the combination together correctly. Okay, so we would take our first function, f of x, x cubed minus 8, times the derivative of that second function, derivative of g of x, x squared plus 4. And then add the second function, g of x, x squared plus 4, times the derivative of the first function, f of x, x cubed minus 8. Okay, and now we'll rewrite a little bit. We've got x cubed minus 8, but for this, for this derivative of x squared plus 4, that is a power rule right there. Okay, so for the power rule, we're going to bring down that 2 as an exponent, or bring down the 2 from the exponent, bring it down as a coefficient now. 2x to the 2 minus 1 power, and then plus the derivative of that constant. For derivative of any constant is 0. So there's the derivative of x squared plus 4. We'll clean that up in just a second. And now we'll add x squared plus 4 times the derivative of x cubed minus 8. So very similarly there, we use the power rule to take the derivative here, bring down the 3 from the exponent as a coefficient now, 3x to the 3 minus 1 power, and then minus the derivative of that constant, 8. Derivative of any constant is 0, so there we go. Okay. And so what we end up having here is x cubed minus 8 times 2x, okay, just cleaning up this term there, and then plus x squared plus 4 times, that would be 3x squared. All right, there we go. And now we have taken the derivative. We've done a little bit of cleanup, but let's do just a little bit more. Let's distribute out here because it looks like there could be some common terms that we could combine. So if we distribute, we have 2x to the 4th minus 16x plus, distribute, 3x to the 4th plus 12x squared. And yeah, there are some common terms that we can combine. We have 5x to the 4th together there. 5x to the 4th plus 12x squared minus 16x for that derivative. So that is the answer. We've taken the derivative by using the product rule. Now we can verify this by using the power rule just to check and make sure everything turned out okay with that product rule. So to verify, we are taking the derivative of x cubed minus 8 times x squared plus 4. And instead of going straight for the product rule now, we are going to distribute out first. So we haven't taken a derivative yet. Keep writing that d dx. Okay. And we're going to distribute out everything inside of there. We'll have x to the 5th, and then plus 4x cubed minus 8x squared and minus 32. Okay, so we've distributed this out into a nice polynomial, and now we can just use the power rule directly on this expression. So when we do that, we are going to get, okay, power rule, bring down that 5 as a coefficient, okay, 5x to the 5 minus 1 plus 4 times the derivative of x cubed, which would be 4 times 3x to the 3 minus 1, okay, minus 8 times the derivative of x squared, 2x to the 2 minus 1, and then minus the derivative of this constant 32, which is going to be 0 when we take the derivative. So we're going to get 5x to the 4th plus 12x squared. That would be right there. Okay, 12x squared minus 16x to the 1st. And then we don't need to write minus 0. But look, it's exactly the same. So that verifies that, hey, yeah, the product rule actually turned out okay. We ended up getting the same answer either way. So we're just practicing using that product rule and making sure that, yeah, it actually works out the way that we're expecting it to. Okay, so let's do one more here. For B, we are going to take the derivative with respect to t this time, d dt. And even though we're using a different variable right there, we have t instead of x, the function here is in terms of t. It's t squared times 2 square root of t plus 1. And so the process works the exact same way, even though that says t instead of x. Don't let that throw you. This just says we're doing things with respect to t because our independent variable in this function is t. And that's the variable that we want to focus on when we're taking the derivative. We want to do all our derivative rules in terms of t with respect to t. So that's what that means. Okay, so we're going to do this with the product rule first, playing with our new rule, our new toy here. So here's our first function, t squared. You can label that as f of x if you like. Oops, except it wouldn't be f of x, that would be f of t. Okay. And then the second function here, that would be your g of t. And that's, again, why I tend to just call them first and second instead of f and g, because then it's easy to say like, oh, f of x, but it's really f of t. Okay. So for our product rule, we'll have our first function, t squared, times the derivative with respect to t of the second function, which I'm going to rewrite that real quick as 2t to the 1/2 plus 1 instead, because we don't really like radicals when we're doing derivatives. It's much better to write those as rational exponents. So there's our first times the derivative of the second function, and then plus the second function. Keep track of those parentheses there, times the derivative of the first. Okay, time to take some derivatives here. Okay, even though we're already in progress of taking a derivative, we'll take these two derivatives inside of the derivative overall. Okay, so we have t squared, and then times, that would be 2 times, use the power rule, bring that exponent down as a coefficient, 1/2 t to the 1/2 minus 1. Okay, and yes, we'll clean that up in the next step. You don't have to write this part like 1/2 minus 1. If you just want to do that subtraction right away, get -1/2. I'm just writing the steps out for right now, since they're still relatively new to most of us. Okay, and then we'll add the derivative of this constant right here, which is 0. There we go. And then plus 2t to the 1/2 minus 1. And the derivative of t squared is going to be 2t to the 2 minus 1. Okay. So let's see, what do we got here? We've got t squared times, well, looks like we get a little cancellation here with the 2 and the 1/2, so that's nice. So inside there is really just t to the -1/2 power. And then plus 2t to the 1/2 minus 1 times, let's see if I can fit this in here, 2t. There we go. And a little bit of cleanup. Let's multiply these together. So multiplying these together, add the exponents. That would give us t to the 3/2 power and a little bit of distribution here. Plus 2t to the 1/2 plus 1 right there. Even though there's not a 1 written, we know it's hidden there. So that would be t to the 3/2 power as well, and then minus 2t. Okay, so combine these like terms there, the t to the 3/2. We got 3 of those. 3t to the 3/2 power minus 2t. And that is our derivative. Okay. Oh, except I caught a little something here. All right, so what did we miss, guys? There's a constant that's off here. If you look back at that last step, or maybe you caught it as it was happening, notice how here, when I did this distribution, 2t times 2t to the 1/2, I was so focused on the exponents there that I forgot to multiply the coefficients. That 2 times 2 should not still be a 2 there. That's going to be a 4t to the 3/2 power. So let's fix that. Okay. Boop. 4t to the 3/2. And so that would make 5t to the 3/2 right here. Okay, did I miss anything else? Yes, I did, actually. So, boy, there are a few things to catch on this one. I think I was moving too quickly. Notice how I dropped a sign back here. Okay, 2t to the 1/2 plus 1 is our actual g of t function. And then, again, I don't know what happened, but that plus somehow turned into a minus on the next line. So we want to fix that. That should be a plus right there, a plus right here, and that plus is going to carry right on through. So we have 5t to the 3/2 power plus 2t. Okay, so these things happen sometimes. And, you know, if you happen to do this in an exam situation, this is what partial credit is for, okay? So don't let that freak you out too much. It can, however, throw things off if you're going to be using this expression later on in a problem. So we do want to kind of keep an eye on things like that. And one of the ways you can do it is to verify your derivative by using another rule if necessary or if desired. If you're a little bit unsure of your final answer, see if there is another derivative rule that you could apply. So in this case, we can actually distribute out our original function and apply the power rule to it. So that's how we're going to verify this derivative. Okay, so the derivative with respect to t of t squared to root t, instead of root t, I'm going to write t to the 1/2. We're going to need to do that anyway. So 2t to the 1/2 plus 1. Okay, that would be if we distribute out, let's make sure I get my distribution right this time. Derivative with respect to t of, we're going to ditch the interior parentheses here. We're going to have 2t to the 5/2 power, because that's 2 plus 1/2. 2.5 is 5/2. Okay. And then distributing here, that would be plus t squared. Okay. So when we do this derivative now that it's been distributed, we're going to use our power rule only. All right, so we'll take our constant multiple of 2 times, bring down the 5/2 as a coefficient, and then t to the 5/2 minus 1. Okay, then we're going to add and bring down this 2 as a coefficient. So plus 2t to the 2 minus 1 power. Okay, so to clean this one up, we can cancel some 2's right there. And we're going to end up with 5t to the, 5/2 minus 1, that's 5/2 minus 2/2. So that is 3/2 power. And plus 2t to the 2 minus 1, which is just 1. So we can see that this actually came out correctly here. And I'd say it was a lot faster and easier to just distribute this one out and take the derivative, less to keep track of, less opportunities for error, let's say. But this is why knowing all of these differentiation rules is really handy, because, you might want to check something like this using a different rule. Or, if I hadn't spotted those errors that I initially made with the product rule here, then I could use this verification as a double check to say, oh, looks like something must have gone wrong because these should really be the same answer. Then I could go back and look for those errors. So there's a couple examples of using the product rule. You will not always be able to verify by using the power rule, okay? Not every function is going to distribute out and play nice like that. But when you can distribute out and use the power rule to check, it's a really nice thing to have.